And Maddie, I did not eat lunch, so I will be eating lunch while we are working on problems today.
That is perfectly fine.
All right. So titration. Titration is where we end up adding a reactant to another reactant. Okay. So what happens is we start out with one of these burettes. We talked briefly first semester about these burettes. They're just essentially like graduated cylinders on steroids. Okay. Super skinny tube here. Each division is 1/10 of a milliliter. And you have what's called a stopcock down here. And you can turn that, and that'll allow this material to flow into the flask down here that has another reactant. When those two things meet, then they start reacting, and you're able to get to some point where you have an equivalence point, and you can figure that out in a variety of different ways. But one of the most common ways is to use an indicator. So, for example, if we had a strong base and a strong acid here, we could put phenolphthalein in our flask. Phenolphthalein indicates when we get a base formed, and that we could put the base in here until we end up forming essentially a base in here, and then that'll turn pink. In regular or in pre-AP Chem, normally I would have you start off with sodium hydroxide in here, hydrochloric in here with some phenolphthalein. You would end up titrating enough into here to get this to turn the faintest of pink colors, and that would indicate that you had reached equivalency. In here, I usually do a titration between a weak acid and, I usually use sodium hydroxide here, which is a strong base. And then I think I use acetic acid in here, or citric acid. I'm going to have to look and see which one it is on the lab. So we'll do something like that coming up, okay? What the equivalence point is it's the point in your acid-base titration in which the total number of moles of your acid, your hydrogen ions, equals the moles of your hydroxide ions from the base, okay? And that works out really easy math when you're doing a strong acid, strong base, because each of those things, ends up completely breaking apart. But when you have a weak base or a weak acid, that doesn't work, because not all of that completely breaks apart. And so then the math gets a little bit of an issue there, okay? So when a weak base or a weak acid is titrated with that strong acid or base, then the strong one wins. So whichever one you're titrating with, whichever one is strong, that one's going to win. So what does that mean? That means that if you have a strong acid and a strong base, the equivalence point, the pH, will equal 7, okay? And that's easy, okay? That's why I do that one in first year. If you have a weak acid plus a strong base, then your pH will be greater than 7, because the strong one is going to win. If you have a strong acid plus a weak base, then your pH will end up being less than 7, because your strong will win, okay? If you have a weak acid, weak base, then you got to look at the Kas and the Kbs and figure that it just gets to be a mess, and they're not going to have you do that this year, so don't worry about it. Again, like I was saying, indicators used to indicate when the endpoint's found. You'll end up with an equivalency point at some, in that area, and you can figure out your titrations and that sort of thing. So when we do this, we always start with one of the concentrations that's known. And then you have to determine from that equivalency point how much you've added in of the other material, and then you can calculate how many moles that was, and then from that you can figure out what the molarity was. And again, we use a transition point, that endpoint. We have some sort of indicator that we're going to work with, and that's going to end up telling us what value that is. Typically, when you are working with these, you want to find a have we talked about pKa? We haven't talked about pKa, have we? So you want to find we have, I'm sorry. So you've heard of Ka, right? Okay. We can also have pKa. So to find the pKa, that equals the negative log of the Ka.
I think we did talk about it.
Okay.
Because it was like on some of the homework.
Okay, so the pKa then, if you find that, you want that to be, whatever the pKa is, you want that to be right around the same range of where your indicator will have its turning point. So you want that approximately equal to the pH where that indicator flips back and forth between colors. And I think it's a plus or minus 1 from the pH. So if it's in that range, that pKa is plus or minus 1 of the pH, then that's usually what you want to pick for your indicator. All right, good. Questions about any of that? Any of that not make sense? All right. One here. Ooh. Okay, let me just save that. Markers in red and important. Okay. All right. So titrations then, typically you'll do them a couple times just to make sure that they're correct. In here, a lot of times we don't have time just because we only have 47 minutes, 46 minutes now. It used to be that we were able to do them a few times for the accuracy. If you get into college, typically your chemistry labs in college are 3 hours long. So you will probably have enough time in there to get it to work. Typically, if you don't mix your solutions correctly, that can be an issue. And with that, usually in here when we do these, I have one of those magnetic stirrers going. You've seen those with the little bead where it turns around. So that helps a lot with this. People will oftentimes overshoot it. And when you're doing these acid base ones, typically you'll have 2 burettes set up. You'll have one burette that has the stuff that you're feeding into the flask itself initially, just to put that volume in there. And then you've got the other one that after you get that acid or whatever it is in that flask, that you're adding in kind of slowly to get the reaction to occur. So if you overshoot it in this one, all you have to do is go back, add a little bit more of this one, get it to flip the other direction, and then come back. So that's why we typically will say, make sure that you put your initial volumes of each of these. And it really isn't a big deal that you start out at 0. I mean, you want it close to 0, but you want to put down what you're starting with. But you may end up having to add more in to flip it back the other direction and go back and forth a few times. Okay. And that's why I really wanted you to have experience doing these acid base ones before we did that other one that I was trying to get you to do this fall. Because with that other one, there was no margin for error. You can't flip it back if you go over it. And so this way, if we do it in the order that we're going to end up having to do it this year, you'll have had that experience with this before we get to that other one when we get to thermochem and redox. Kind of a review of redox. We need to review redox before we can do unit 9. All right. So again, you can add 0.02 mils or less. That's actually less than a drop. And you should try to get within a 0.1 milliliter agreement between your trials. Okay. So you try to get it within that kind of ballpark. That's kind of the industry standard, so to speak. All right. So our first example here, we have NaOH. We're going to be neutralizing 0.25 of this standard KHP. And they want us to calculate the NaOH involved there. All right, so step one, we're going to figure out we've got 0.1072 molar of this KHP. And we want to figure out how many moles of that we have. So I'm going to take that and I'm going to multiply by this volume. But before I can multiply by this volume, what do I need to do to it? Convert it into liters, right? Because remember, molarity is moles per liter. So I have to turn it into liters to make it work. Okay, otherwise this, if I change this to moles per liter, you can see why I need that. Because molarity is moles per liter. So if this is moles per liter, now my liters are going to cancel, and that's going to leave me with moles of this KHP. Okay? So do the math there. I end up with 0.00268 moles of this KHP, which means that I need to figure out, so standardizing solution finds that we needed this much to neutralize this stuff. So I had this many moles of this. I needed this many, so that many moles of that will equal how many moles of OH I will need. Because remember, if we're standardizing this, they have to cancel each other out. That's the whole idea. So OH ions. So I need to divide that by how much of that I needed, which is 0.02815 liters. And that tells me my molarity. If I do the math there, that ends up being 0.0952 molar NaOH. Good? Everybody happy? All right. So when we are doing these, the majority of your titrations you'll be expected to perform will involve determining the solution concentration, the volume of that solution, molar mass, and then percent purity is also some of them. Okay? So regardless of which acid or base is involved, the total number of moles of your H plus equals the total number of moles of your OH when you're at the equivalency point. That is what the equivalency point means. Okay? Equal number of moles of H plus and OH. And if this comes from a weak acid, then it's going to take a lot more of the weak acid to get to that point. If this comes from a weak base, this comes from a weak acid, it's going to take a lot more moles of that to get to that point because it only gives off a very few of these H plus ions. Does that make sense? So step one normally involves using the data to determine the number of moles of the reactant species used. Remember, if you have molarity, if you multiply molarity times volume in liters, okay, that is going to equal your moles of material, whatever it is. Okay? So multiply these. You can kind of think of that as one of those triangles. You guys had the density triangle back in the day, right? If you have molarity times volume, that's going to give you moles. If you want moles per volume, that's going to give you molarity. Okay? Does that make sense? Okay. Moles divided by molarity gives you volume in liters. This has to be in liters if we're talking molarity. Second step then uses those moles in the first step and a mole ratio in a balanced equation to determine the moles of the second reactants consumed. And then the third step uses those moles to determine a concentration, molarity, and volume, liters, molar mass, or percent purity. All right. So we have a 25 mil sample. What is this? This screams to you what?
Acid.
What kind of acid?
A strong acid.
Strong acid. And what does this scream to you? Strong base.
Yeah, strong base.
Okay. So strong acid, strong base, equivalency point is going to be 7. But they need to know if we've got this sample, how much of this we need to get it to that pH of 7. Okay. So step 1. When we are doing this, we need to figure out how many moles we had in this sample here. Okay, so 0.203 molarity. Remember, that's moles per liter. If we multiply that times this in liters, so 0.04623 liters, that's going to give me moles of OH minus. So that ends up being 0.00938. Everybody cool with that? Okay. Since this is a strong acid and a strong base, this will give off as many hydrogen ions as it started with here. So I need to see that I have 0.00938 moles of OH. That will equal my moles of H plus at equivalence.
Symbol for equivalence.
Huh?
Like a kind of like the not like an equal sign, but something like an equal sign when it is at equivalence.
Like this?
Yeah, that one.
That means approximately.
Okay.
That doesn't mean that, it just means that you're about at that amount.
Okay.
Okay. So at equivalence, this should equal this. And that, since these are strong acid, strong base, that's going to happen at pH of 7. Okay. So when we look at that, then we know that we need 0.00938 moles of H plus ions. I know that for every 2 moles of H plus ions I have 1 mole of H2SO4. See the 2 here? That's where I got that 2 from. And if I want molarity, what other component do I need? Liters. Okay. So I know that I need liters on the bottom, right? Okay. So I know that I used this much. So I need to convert that into liters, which is 0.0 0.25 liters. Okay, so my moles of this will end up canceling. That's going to leave me with moles over liters for H2SO4. So I just divide this by 2 and then divide it by 0.025. And I end up with 0.188 molar H2SO4. Good? Makes sense? Okay. So now we're moving on to solution volume from titration data. You'll probably be given concentrations of both the acid and the base. If you're not given the concentrations directly, then they'll give you enough information to be able to calculate it. Final step in the solution process involves converting the moles of a reactant determined in the second step into a volume using those concentration values. So make sure that you have a reaction that goes to completion. Volume of the standard solution required in the titration is only dependent on the stoic. Love your stoic, right? And the moles of the species that must be neutralized. It doesn't depend on the strength of those species. All right. So here we have, again, a strong base, and we have a strong acid. Where is our pH equivalency point going to be?
7.
7. Okay. All right. So not that that really matters. That doesn't come into play at all for solving the problem, but it's just a good thing to get you kind of used to thinking about. Okay. All right. So when we're looking at strontium hydroxide, we've got this for our pH. We know from the stoic of this that we're going to, if we look at the reaction here, it's going to be 2HCl plus SrOH2. That's going to come together to give us SrCl2 plus water. The neutralization reaction, we're neutralizing an acid and a base, we're making a salt, and we're making water. Okay. I need to figure out what concentration of HCl, I'm sorry, they gave me the concentration, my bad. I need to figure out how many moles of this I used in this reaction, okay? So that's going to take me here. I'm going to multiply this times what to get my moles of HCl? 0.025, good. That's going to give me my moles of HCl, which I'm going to put into my table here. And that ends up being 0.0106. All right. How do I calculate how many moles of strontium hydroxide I need?
Divide that number by 2.
Divide it by 2 and then multiply it by 1 when I bring it down here, right?
Mm-hmm.
So 0.00529. So I need this many moles of strontium hydroxide to make this work. Okay. So my concentration of strontium hydroxide okay, I need to have my concentration of hydroxide divided by 2 here. And the concentration of the hydroxide, where did I get that value from? I think I got it from here. Just give me 1 second. Second, negative 13. 14 point, no, it would be 0.5, wouldn't it? Because I need to use the foot. Yeah, that's where I got it from. So if I take this away, okay, if I take this away from 14 minus 13.5, that's going to give me my POH, yes? Okay. And if I take, so that's going to be 0.5. Everybody okay with that? Haven't lost anybody? So then if I take 10 to the negative 0.5, that's going to equal 0.316. Okay, so this standard solution will have this molarity of OH ions in it. Did I lose anybody? I can't tell with the math's on. Are you guys lost? You have no idea what I'm talking about?
Is 0.316 just negative 0.5?
Yep, 10 to the negative 0.5.
That's the molarity of the OH.
Molarity of the OH. Yeah, so that because this is a strong acid here, okay, if this is our pH, okay, that means that every bit of this, when it pulls off, is going to give me this molarity, okay? But it gives me that times 2 because of this. You know, this is a negative, a plus 2, and this is a minus 1. So we have 2 of these for every one of these. So that's why we got to divide it by 2. Okay. And then, so that's going to equal 0.316 divided by 2, which equals 0.158 moles per liter. That's the molarity. Molarity is moles per liter. Okay. So if I need that, that's going to equal, I need this amount here. Okay. So that's how many moles I need. And we're solving for how many liters that would be. Because they're asking us what volume. Okay. So 0.158x will equal 0.00529, and then x will equal, yeah. So then my volume should equal, I'm running out of room here. And this is going to be 0.00335 liters. That's how much of that I'm going to need.
So X is volume.
Huh?
So X is volume.
Yep. Yeah, because molarity is moles per liter, right?
Well, no, I was just looking on like the bottom one. You went from X to volume.
Well, yeah. Yeah. X is, yeah.
So, I had 29.8. I'm not gonna lie, I don't know if I did wrong. So you take the 0.158 divided by the 0.00529, correct?
Yeah.
Okay. Let's see.
For which one did you do?
The 0.158.
No, point 0.00529 divided by 0.158.
Oh,
Yeah.
I see what I did. I gotta divide.
Yeah. This has to,
158, not the-
yeah. We're trying to get X isolated.
Okay. There we go.
So if we isolate X, then, which is your volume, that's your volume of the strontium hydroxide.
Mhm.
I know I got that a little muddled up there with a lot of lines and I talk a lot.
Okay.
All right, good?
Mhm.
Want to make this stuff go away? Cadence, you good, hun?
Yeah.
Okay.
This is kind of relaxing to watch it all race. Just looks cool.
All right. So when we go through these titrations, we're going to look at our pH. We're going to be looking at when we end up with these indicators and kind of how they work. An indicator is a buffer. And so we need to kind of digress and talk about buffers. And we're going to spend some time doing that coming up. So I've got a couple of different ways that we're going to kind of look at this. We're going to look at it first through the lens of these indicators, and then we will look at it through like just actual buffer problems. Okay. And then that's probably a good place for us to kind of stop today. And then we'll pick up with this tomorrow. I do want to give you some notes on buffers just to get that in your hands depending on how fast this goes. So I'm going to try to get those printed out before you guys leave and get those into your hands, okay?